Okay, how's this?
Yep.
Okay, cool. All right, so I'm going to start. I think we have a couple of people who are, if you don't mind muting your mics so we don't get any feedback, that would be great. So, hi everyone, welcome back to another IoT seminar. There we go. As a reminder, these sessions are recorded. Welcome, Bill. Good morning, good evening, good night, and wherever you are. As a reminder, your market research and costing plan is due this Sunday, 30th of May. We did cover this extensively in Seminar 2, so if you've missed the seminar, I would recommend going back and watching that, where we went through the point of what you should be covering for this seminar, for this assignment. By now, you should have received all of your marks for the video submissions. Well done on those. We had a couple of very interesting ideas. As a general note, I would say most people have to slightly focus more on the unique value proposition to try to highlight it a bit more of what unique factors your product can provide to the market. But overall, they were pretty good. I've given feedbacks to you. If you haven't received any feedbacks, let me know and I'll send you the feedback again. So as always, use your team as sounding boards for developing and prototyping your ideas. We have the market research and costing plan due, as we mentioned. As a reminder, this is going to be 15% of your overall marks. You get 25% for the industry analysis, 10% for the competitor analysis, 30% for products and services, 10% for pricing strategy, and 25% for your SWOT analysis. And as I said again, we covered this during Seminar 2, so I do recommend going back and watching that. And this would be a good point to kind of keep building that the Cavanizer that you've been working on, and keep building on it, and especially after the market research and costing plan. And by the time we get to the final report, this would be a good resource to use the Cavanizer that you've been keeping adding to it for that final report. Now, heading towards production and for our seminar, now we're going to be talking a bit about software development tools for custom PCBs, and a little bit about the housing of your product. So now that we have a good idea of how we would go about prototyping using development kits, we have a good understanding of sensors. Let's see how do we go about actually developing the software component of these IoT devices that and the IoT idea that we've been thinking about. So let's start with why we shouldn't be using Arduino's IDE. Now, first, let's talk about the good things about it. Arduino IDE is good for very early, just functional prototypes if you just want to see if a sensor functions. Now, the problem with Arduino IDE is the fact that it's because it's been built towards hobbyists, and the code you end up writing with them, it has to support a broad range of hobbyist type boards. The codes that you have in there, they're not going to be the most optimized code in the world. And why is that? Because to make things simple, all of the setup and all of the library functions would have been already defined for you. All of the pin headers, all of the internal connections and peripherals would be defined in the library file. So what you're basically doing in the wiring language code of the Arduino is you keep bringing function calls to those variables, and say, as you can see in this very simple code here, this is for blinking an LED. On the surface, yes, the code is very readable. We're just doing a digital write. We are waiting, so with a delay function and digital write low to get a blinking function. Now, the problem with that is, while we're doing this digital write, we're also enabling lots of peripherals that we don't need within this code. So it wouldn't be the most optimized code in the world. And also, we don't have any debugging functions available to us. You wouldn't be able to monitor what's happening on the low level. You wouldn't be able to monitor what's happening with your registers, your memory blocks, and things like that. So that's why we use stuff that's a bit more complex, like Code Composer. So when you get close to to your product and your idea being an actual product that can be useful, you want to write the optimized code. And for that, you need something like Code Composer, IAR, or I think that the name skips me, the development kit that comes with the STM boards. Now, the benefits of these devices, in addition to them giving you the tools for writing more optimized code, because you will have access to assembly language. For those of you not familiar with assembly language, assembly language is basically the lowest level of programming language that we have that's closest to the machine code. So when the ones and zeros that you have stored inside your computer architecture's registers, those get transferred to hex values, and those values, we use assembly language to write the conversion for that. So imagine a simple A plus B plus C code in C could be multiple levels and multiple lines of assembly language. Why? Because assembly language deals directly with that hardware interaction. Now, you might be wondering, why do we need that low level of interaction with the hardware? So that's the point, because you want to write optimized code. An example of a code that I can give you is, let's imagine a temperature monitoring system where we're constantly monitoring temperature of an environment. And what we want is, if the temperature raises above a certain level, say about like 40 degrees of Fahrenheit or 40 degrees of centigrade, you want the warning light to turn on. Now, for you to be able to do this operation, what you need to be doing is you need to constantly monitor the temperature. So in an embedded system environment, which is when you're dealing with a system with limited resources, your code will be running in series. You usually don't have multiple cores in your processor to divide the tasks. So what will happen is, what will happen is your code is running. You need to stop the code from its operation, which is constantly monitoring the environment's temperature, to do something else. This something else is the rise in temperature. That's what we call an interrupt. So what needs to happen is your current state of the program needs to be saved somewhere. You go to a different part of your program, handle the interrupt event. So again, the interrupt event is the rise in temperature. And what do we do when the rise in temperature happens? We need to turn on an LED. So we turn on that LED, we turn on that warning light, and then we need to go back to our initial stage. Now, for us to do this whole process, to handle this interrupt and to be able to save my current state of the program, I need to have access to low-level code so I can know exactly when I should be storing my, where I should be storing my current state. And if you're interested, we're going to be using the stack to store the current state. So we push the content of your instruction there. We go to a different part of the memory, handle the instruction, go back. Now, when you're dealing with such a low-level interaction with your computer architecture and with your microcontroller architecture, we need to have access to this low-level coding. So this part of the code that Ian has highlighted here, this is an example of interacting with the timer counters of our microcontroller with an assembly language level. Now, with these
Sebastian.
Yes.
Yeah, when you're finished, I've got an example of a very simple for loop in C and how it converts to assembly. So that actually shows it quite nicely.
Okay, thank you for that. And that's actually to that point, with these IDEs that are a bit more complex, you will usually have the C-level code, and you will have a disassembly window that will show you the same line of C code. How does that get translated to the assembly code, and then what is the exact value that's inside in your register? So if you look at the left-hand side, we can see that we can monitor a couple of the registers. We can see all of the files that are connected to our current project, and you can see what resources with this diagram in the middle. We can see what resources we're actually using to actually write our program. So the code ends up being much more optimized. And so, Ian, did you want to share that example now or after the presentation?
Let's do it after. Easier than trying to.
All right, sure. So, well, now that we know how to write the good and well-optimized code, next stage is, let's head towards production of the hardware component. Now, what you see here are two examples of, we briefly mentioned in our last seminar, where we where we have a development kit that we're literally sticky taping on top of a couple of other development kits and just putting them in a case. And of course, you don't want them official product. You don't want to open up a product and see something like that, right? You want things and to be designed very nicely on a single printed circuit board, like the one that we have on the right-hand side, and use that in your device. So the next step is when you're done prototyping, when you're done designing the hardware components and choosing the connections using those development kits, you want to design a PCB that has all of those components in there. Ian, the one on the right-hand side, if I'm not mistaken, is that the text-to-speech dedicated PCB that you worked on, right?
Unmute and it might work. The small square board on the left is the text-to-speech. The one on the right is a ultrasonic guide for people with vision impairment.
And there's an interesting point about this little tall crystal that you see here that we'll get back to it. Now, we have lots of interesting tools that you can use. One of those examples that's readily available for free is called FRITZING, where you can draw the schematics and you can even draw the, say, if you're using an Arduino, use the 3D model of the Arduino, make your connections, and with that schematic, you will get the PCB layout, and then you can even straight up order the board from the same company. Now, the problem is if you go to this route, the actual board ends up being a bit more expensive. So usually what we end up doing is, especially if it's for some of the initial prototyping, you would design the file and you would design the PCB, then use one of the Chinese websites like a PCB JLC, PCB, and PCB GoGo, which will show an example of how that would look like, because they will produce a lot of them for you, and they can even produce them populated, which is you get the PCB with all of the individual components already mounted on there. Now, remember I said there's an interesting story about that. Now, with these types of prototyping, I think Ian mentioned we have about 30% failure rate, but because the cost is so cheap, that's okay. We can afford to have 30% of them not work, but of course it's wasteful, but it's good for early prototyping. So because of that, you'll get an idea, even though we had mentioned in the design that we want to use a lower casing crystal, they ended up using a taller crystal because it was cheaper to manufacture. So when we got that in, we couldn't fit it within the casing that we had built for it. So it took us some time to unsolder this, replace it with a shorter casing crystal, so we can fit it within the cases that we had. But we'll talk about the cases in a bit. Another one level higher and one level a bit more complex and robust program that you can use is Eagle. It's provided by Autodesk. There are limited versions of this available, and usually one of the main differences that you get with this compared to more complex stuff is the amount of PCB layers that they will allow you to build. So with the free and trial version of Eagle, you can go up to 2 layers, and it's scalable. It is cross-platform, and most of these PCB design IDEs will allow you to extract your designs as Gerber files. And this is a universal format of the PCB design files, where when you go and you want to manufacture the PCBs and order them in, you would need those Gerber files. And of course, you have the very high-end applications, which is this one is Altium, that will allow you lots of robust tools and lots of 3D representation of your circuits. You can go to multiple layers, and I think the license for this one ends up being something like $10,000 a year or something like that, if I'm not mistaken, Ian. Is that correct? Is it about 10,000?
Yeah, I'm forgetting you can't see me doing thumbs up. Yes, that is correct.
Mm-hmm. And one of the biggest difference with something like this and the previous ones, in addition to allowing you to go to multiple layer, is the fact that with PCB design, we usually draw the schematic and then do what we call auto routing, which it would give you a very rudimentary connection between all of your components. Then we go and fix that and make sure the ground planes and your signal planes and your power planes are separated from each other. And with tools that are a bit more robust like this, that auto routing is much more better, much more reliable. And of course, we have multiple layers. You have a lot of more information, and you have a lot of more flexibility on how you're designing. And of course, there's a lot more customer support with something like this, where because you're paying so much for it, they will support you in the design stage as well. So I think, yeah, so this is an example of what sort of is this. Yeah, so but at the end of the presentation, we'll show you a couple of examples of going to a PCB ordering website, and you'll see what sort of options you have available to you. Now, you can either order these PCBs as just the PCB layout and solder the components yourself, and of course, these days with so many SMD and surface mount components that we have access to us, we could as well just order the components and order circuit PCB already populated with the components already mounted there. And they usually give you a couple of options. You can order the PCB with when the manufacturer of the PCB sources the material, or you actually source the material yourself. So I mean, source the components yourself, which of course it's a bit of a challenge these days with the chip shortage that we have. So as I mentioned last time, this is probably another consideration to what you would typically consider when you're thinking about that PCB design stage. You have to look at you have to look to see what chips are currently available. So maybe the one that you really want and works very well, it might be out of stock because of the kind of silicon shortage worldwide. And here's another slide showing you some of those options, and we'll go over to the live version of the website and show you. And we do, I think, if you can already see, this is a 100 by 50 millimeter side, 6 layers, and all of the typical default settings. As you can see, the cost is like, for how many did Ian put in? For this is just one quantity for 5 of them. This is about 185, and this is kind of going maximum to 6 layers. So if it's a very simple design up to 2 layers, you're going to see that the actual cost of manufacturing is going to be lower than what it would cost you to ship the board to yourself. And of course, we have the housing all of these PCBs, and we have a couple of different options. Ian, do you want to take this one? Because I think you have a bit more experience with GFI boxes.
Yep. 2 seconds, I'm coming back. I was just looking for a PCB manufacturer.
Yep.
Okay. Yep. So once you've actually got your PCB laid out, you really want your device to be in a housing which is suitable for sale, unless it's going into a industrial setting or a setting where you're not going to be looking at it. So you want to move away from the cheap off-the-shelf boxes, possibly, to something a little bit more useful. So before you, hopefully this will work with, come on, camera. This is the controller from my Oculus Quest, and it's all nice and smooth. There's no rough edges. The buttons are all in the right place, and it feels as a controller should do. In the early prototype stages, it may well have just been a standard joystick, or even just using a keyboard instead to simulate that sort of process. So that's one extreme, and the other extreme is the simple type boxes that we use for prototyping, but can also use in industrial cases. The GFI box is your typical one. These are, number one, very, very cheap. They're a matter of $1 or $2 each. They're ugly, but they can also be made weatherproof. And weatherproofing or sealing things to be at a suitable level for the environment they're going to be in is a critical thing to think about with your case design. I'll use an example that we had of an external housing that was quite large for some power electronic equipment. And they designed it all really well. They used the right sort of seals and connectors on it, but they went and put the cable, the power cable, into the top of the housing. And that meant every time it rained, moisture would gather around the cable, gather at the weatherproof seal, but still slowly leak past that seal because it was coating the cable. And it was dripping inside the power electronics and, of course, ended up destroying them. And it would have been very easy to solve that by putting a cable in from the side, but they just didn't think of that at the time. Another really good example is designing a housing to go on a firearm. This is going to be used by soldiers, and there is one thing that nobody has ever worked out, and that's how to make something soldier-proof. They are really, really destructive. And of course, that's going to have to be hardened or ruggedized. So the materials you use will be completely different for that device to go on a firearm, sensor on a firearm, than what you would use, say, in a Oculus Quest controller. So we started with the Jiffy box, cheap, easy, easily available, and lots of different sizes. If you want to do something a little bit more marketable or a little bit more towards production, 3D printing is a really good way to go. That top diagram is a 3D printed Raspberry Pi case, I think, from memory. And if you look really closely at it, you can see the lines that have been created when you use a FDM. That's a standard filament type deposit 3D printer. It's got little jagged lumps on it where a glob of plastic is stuck. It can warp. And probably the most critical factor with 3D printed, this style of 3D printing anyway, is strength. Because it's layered and you're putting one layer on top of another, on top of another, it has a reasonable amount of strength if you bend it along the lines of the layers. But if you print the wrong way, so if we've got something flat, yeah, that'll look something flat, and we print across this way, going horizontal to the length, and we bend it, it'll snap. So they don't have a great deal of inherent strength. The materials you can use are also limited, reasonably limited. Most people would use either ABS, which is quite rugged, but it can warp. PLA is another one that's used very often. That's a modified cornstarch. So it has the advantage it can decompose if you treat it correctly, but it becomes brittle with age in a very short amount of time, in fact. So if you print a PLA coffee mug, it's not going to last very long. The next step along is rapid prototyping. This is somewhat like 3D printing in that they create a machine mold or some other method of rapidly producing a production quality appearance. It usually doesn't have the strength of the finished device. It's used for display only, but you could use those ones for fitting your components in, making sure everything fits, check the ergonomics of the device, make sure that if you've got a keyboard type layout, the keys fall to hand correctly, and those sort of general testing, much like you would with 3D printing, but the quality of finish is much higher. Finally, we've got the stage of injection molding. This is where you get very high quality output at a very, very low price per item. It works simply by having a mold, which we can see by that little chest piece in red down there. We inject molten thermoplastics into it or some molten material, and we get our device out. As I said, really, really cheap per item, but the setup cost is incredibly expensive. I used to have a company that manufactured these type of dies. The reason we did it, we actually manufactured very early robotic machining tools, so CNC machines, engravers, that sort of thing. And we'd actually build these sort of dies for cash flow because we didn't sell too many of the machines, they were too expensive. So we were manufacturing these, and a very low cost one would be around 40,000 Australian dollars. So you've got a very large setup cost, but a very low per item production cost, which means if you're going to produce 10,000 of these little widgets that you're making, injection molding is a great way to go. Costs have come down a lot since I was doing it because of the automated machinery for producing them, but it is still very, very high. But again, if you've got the numbers, it's worthwhile. Oh, I didn't do vacuum casting. Vacuum casting is another one. You see this a lot in the forming of, say, punnets for seedlings.
Trouble hearing you.
I wasn't talking to you, Siri. My watch just went off. So you see this in, the punnets where you buy seedlings at the nursery. And it's a very simple process, again, with using sheets of thermoplastic. You heat that up, you pull it down over a mold, and then you use a vacuum to actually suck it into place on that mold. It's relatively good. It's very cheap because the tooling cost is fairly low. But again, you have an issue with structural strength. Usually the material used is very thin so that the vacuum can pull it down correctly. And it has to be a low melt thermoplastic, which tends to mean that they aren't very strong. But again, it has its place in producing very cheap, lightweight containers. I think that's about it. So I'll hand back to you, Sebash.
Yep. Thank you, Ian. So, okay, so that covers it for this short seminar, and we'll show you a couple of PCB manufacturing website, and there's a interesting 3D printed motorcycle frame that they use for that rapid prototyping that Ian was mentioning. So our next seminar, David McMeekan, he'll give a talk about spatial sciences concepts and looking at location data and using some of the APIs that are available to us. And of course, as a reminder, we'll be running the MOOC for 2 extra weeks. And by the way, something I forgot to mention at the beginning, if you haven't gotten responses back to your emails, please feel free to send that to us again. If you don't get a response within say 2-3 days, feel free to forward that to us again, so it pops up in our mailbox, and we'll get to it as soon as we can. Okay, so let's have some discussion. Well, since I'm sharing the screen, actually I have to share.
Okay, I can put the links in that I've found.
All right, sure.
I just ran while you're getting it up and going.
Sure.
I just did a quick PCB GoGo quotation for for 10 30 by 75 millimeter 2-layer boards, pretty standard. For 10 of them, it would cost us $5. Unfortunately, the freight is $24.
Yeah.
So you can see the manufacture of PCBs is really, really cheap to produce custom PCBs. When, again, if we look back at your costing, the process to develop them, particularly when you get into something a little bit more complex, which is probably a good one for you to do there, Savash, do a 6-layer board or something.
Yeah, so let's see.
To actually design that, to design that and have the software capable of creating it, and to have the skilled people lay the PCB out so that you're not going to get RF interference, you've got your ground planes in the right place, signal paths are separated sufficiently, it's going to cost you far more than actually producing the board.
Yeah, and then
boards, easy.
Yeah, so as you can see, so I changed it just from 2 layers to 8 layer with everything the same. The cost jumped from like $30 to $302. And as you said, they offer different types of facilities, like the PCB assembly one, where you can source the material. Another example that I had going, so this is PCB GoGo. This one is PCB Way. Again, fairly similar. And again, actually, they've added an option for rigid and flexible PCBs that might be worth kind of looking into.
Actually, might be.
Yeah. So what else do they have? Again, assembly, and yeah. So this one, they allow you to have a couple of different ways of assembly, where you source the material yourself, or you get PCB Way to source the material for you, where you might have the problem like the tall crystal that we showed you. Another one, JLC PCB. Again, similar type of settings. And there's FRITZING. I'll post this link in the chat. This one shows you, this is just a tutorial directly from FRITZING that shows you how you go from the basic schematic design to drawing the PCB and then eventually ordering it through FRITZING. So I'll post that in the chat.
Yeah, I would recommend having a play with FRITZING. It's a really nice tool, right through from simulation to building a board.
And we open up that YouTube video I found. So I think this is the one. It's a fully showing the 3D printed.
This is how it does metal printing.
Yeah.
By the laser at the metal paste. So this is a level you can get with 3D printing. The bike here they use to design their production line, I believe. If it's the same one I found earlier. And the entire thing is 3D printed, and they just ran through and assembled the bike along the production line to see if it would actually fit together and to make the production line efficient.
Yeah. Yeah, and it's actually, I didn't realize this is a BMW manufactured. I think there are some close-ups.
BMW.
BMW. Some interesting articles. I'll share these links in the chat as well. In case anyone's interested.
I'll just share mine if you like in a sec. We'll tell me when you're ready.
Sure. I can
share content.
Oh, okay. I need to stop sharing. There we go.
Okay, so we should be able to see that little bit of code here. So we have at the top the C code, which quite simply just calls a function. All the function does is just assign one parameter to another parameter, and that's it. If we look down at the assembly language, it's quite a bit longer. So this, when you type in your C like this is what it gets turned into as an interim. And each one of these assembly language programs is dependent on the platform you're using. So if you're using an Intel x86 processor, these particular mnemonics are different to the ones that Motorola would use. So you have to use completely different mnemonics to program. So if we look here, this is push the frame pointer. So this is telling it to put the frame pointer that's pointing to a particular location in memory to push it onto the stack. If we look down here, this is how we add something to the stack pointer. So we're adding the offset of 8 on the stack to the stack pointer. So each step the CPU has to do has to be in here as a single statement per line. Right, so the CPU running at 1 megahertz, 1 million clock cycles per second, would execute one of these statements every millionth of a second. Whereas if you look back up here, it's much clearer to humans, but it can be interpreted in different ways. When we look down here, we can actually go to every step the computer is making and decide, is that necessary? Is there a more efficient way of doing it? And it's also my favorite language, assembly language. The other thing I was going to mention too is we're talking about how Arduino is not a great platform for real development. Well, Arduino realized this as well, and they've created Arduino Pro. And these are actually a professional level development system, including the IDE, aimed at production IoT. So that's worth having a bit of a look at. At the moment, we're going through the process of becoming an Arduino Pro Academy, so we can actually offer formal training on this platform. Back to you, Mr. Sabash. Yep, muted. Remember, stop sharing screen at mute you.
Yep, right. So I was just going to add a quick point. So in addition to the Pro IDE, they're also releasing a 2.0 version of their current one, and that one's available. We can download it now. The beta of that is out. That does have a couple of pretty interesting debugging tools. So it does allow you to monitor registers and look at some very limited memory content. So I think I've been looking at it in the past couple of days. It looks promising. They do kind of keep up with it, because Yeah, especially I think especially when the STM boards become so popular these past couple of years, and their IDs are so much more robust, and they give you lots of interesting debugging tools for most essentially for free most of the time. That's why I think Arduino is going to try to step up their game, which is well good. It's always good to have competition, but otherwise we would have probably been just stuck with the same idea as before. Okay, so that's I think all of the content that we wanted to cover for this seminar. So feel free to ask us any questions, give us any updates you want to share about your project.
They're very quiet, aren't they?
Yeah.
Everything must be perfect. You must have finished, got the prototypes up and running, and
I see Nuncio. Yeah, go ahead.
Oh, no, I have a question about I'm facing a little bit problem with the ultrasonic sensor for level measurements. I was checking also on internet because I was looking to use a ultrasonic sensor to measure the level tank, and I discovered that many people say they complain about this because the sensor start to give errors and measurements due to the humidity of the tank. I don't know if I was looking for capacitor level type of sensor. I don't know. Have some suggestion about.
my suggestion would be, and I'm just going to go off and look at something as well while I think of it, is to add a humidity sensor and use that to recalibrate your ultrasonic. The other option is, of course, you can use the infrared laser, same as they use in the levels and measurement tools. You buy them at the hardware store, but you can get the components for that. And the components for the laser measure should only be $20 or so, because they sell a complete measurement device for $29 at local hardware store. Let me just go to that. Any other thoughts there, Savash?
Oh, I was going to mention humidity sensor as well. But so Yiffy has been working with using ultrasonic in a kind of tiny robot. So if you wanted to, if you send us an email and put Yiffy in the subject line, he can also, because he couldn't be here tonight, but he might be able to offer some advice as well.
Okay, I will drop the
Okay,
email.
thank you. So I'll just, if you just put Yiffy, I've typed his name in the chat. If you put his name in the subject line, I'll point it to him.
Okay, I will check.
So is it just those normal Arduino module ultrasonic sensors that you're using?
Yes, I was planning to use for the prototype the Arduino ultrasonic sensor,
Yeah.
but I was looking for maybe when I plan to build the first system, the real one, I would say I need to be the caution about the reliability of this sensor.
I've just shared a graph, a link to a paper that talks about this. Let me just share the screen again. And this is the joy of data sheets. Data sheets should be your best friend. So if we look here, this is a data sheet, sorry, a paper on ultrasonic sensors. This, if we look here, we can see that as the relative humidity goes up in response to the temperature, we get a change in the meters per second, right? And it's quite a dramatic change there. So you can then recalibrate based on the temperature and humidity, what the change in the reading is going to be, and correct it. Now, the problem is that going to be accurate enough to measure millimeters in depth of a tank? Maybe, maybe not.
Yeah. because there are
contact link you can have a look at.
Yeah.
This one is yeah. There we go. Good old Banggood. Laser range sensor module. That way it's not going to be affected too much by humidity. Certainly not the kind of humidity you get in a tank.
Yeah, I don't think to reach too high values of humidity in the tank. Maybe around 70%, 60%. That will depend also on the temperature. But the idea to compensate the level measurements with the humidity sounds good.
Yeah.
It's a kind of compensation. Because I have two points for the level monitoring. One is monitoring the level just to maybe to activate the pump. And the second is maybe I was thinking to measure the flow, the collecting flow coming from the rain,
Yep.
from the roof, and this maybe need to be a little bit more accurate. I'm not looking for high precision, but unless to have a good correlation of the flow.
Yeah, we showed those water flow meters previously. We've used them in our water meter project. You could use that, or you could even use a homemade wheel. There's lots of ways of measuring the water flow.
Yeah. I'm also planning to install the flow meter, but maybe after the pump to measure the quantity of water I'm sending.
Yep.
And because the pipe will be filled, when I collect, I'm not sure if the pipe will fulfill it of water. And I don't know if I get some error in this.
Well, the other option is you look at the volume of water you're pumping in, and you use another flow meter to measure the volume of water being pumped out, and that will give you the level in the tank.
Yeah, that is another option. Yeah, I'm checking as well.
Okay, I'll stop sharing my screen. Anyone else have questions? Something they'd like answered?
Yeah.
Meaning of life, the universe, and
Yeah.
everything.
Yannick,
We've
any
got hope for the
update?
universe.
Yeah, go ahead. Eduardo, go ahead.
A small question regarding this week assignment regarding the market search. I'm currently based in Italy, and solution for smart greenhouses are pretty limited. Should I focus on the general market share of the international solution, or should I focus on the national one?
Very much depends on where your market is going to be. So if you're aiming for something that is unique conditions in South America, isn't it?
Italy.
Yep. Then Italy, sorry.
Yes.
I don't know how it got that. It was because of the coffee growers that we've got in the course.
Yes.
That's what it was. Yep. So if you're looking at something that is unique to the Mediterranean climate, then you would only look at a market in that Mediterranean environment. If it's something more general and would handle snow and ice and things in Canada, then you look at a global market. So very much depends on where you think it's going to end up.
Okay, got it. Thank you.
Yeah, it's like if we're developing something in Western Australia for West Australian mining. In many cases, the kind of mining we do here is unique, particularly the open cut because of the scale. So you would design something for Western Australia on its own and not really look at markets, many markets outside of Australia, maybe in Queensland, Northern Territory, where the scale is the same. But it certainly wouldn't be applicable in Europe. You wouldn't have an open cut pit that's 2 miles across.
Or even that our water monitoring project, because in Australia, the actual water meter is outside the house, whereas if you look at places like the States, I think in Canada, they're usually in the basement. So
Otherwise, they'd freeze.
yeah, so there we have that problem. And then another thing that we have, because they're outside the house, powering up the sensors that we're going to have in there is a different discussion compared to if they were in the basement. You could probably just plug them in to a power plug nearby.
And we don't have a freezing problem. Water pipes in Australia don't freeze. They almost boil, but they don't freeze. All right.
Well, I might have another question, but
Yep,
it is related to the course. So if I remember well, in the last seminar, you said that you're going to merge some groups in order for the participant to interact within each other. Are you going to do that, or has it been postponed or something? I'm referring to the teams.
Yeah, I know. We forgot that. Can you look at that tomorrow or Saturday if you get a chance?
Sure, I'll do that.
Thanks. Thanks for reminding us.
No problem.
I think you can still discuss those questions in the general discussion board. So,
yeah, actually, that might be the easiest way. Just go to the general. So can you put an announcement out just saying use the general discussion, because the numbers are probably better in there rather than broken up into groups. The first time we ran this course, I think we had 100 and something students. So it was really necessary to break up into teams. But we've got 30 this time, so it's easier to handle than just one, I think.
It just reminded me of the 100 videos that I saw in 2 days.
Yeah, it was good, wasn't it? I enjoyed it.
Yeah.
Because you did it.
Yeah. And it was interesting. We got a lot of different types of projects, from the horse mucus to...
I got to see the really good ones.
Yeah. We have very Yannick, is that your project, the toilet paper replacement one? Yeah. I think you're muted.
It's
but
still
yeah,
muted. Yeah.
That's one of the interesting ideas.
It is. I could see it. Because not many people think of that sort of stuff, and yeah, it's got definite market value.
Yeah. Yes. Sorry, I was on mute. Yes, it's my project. It's my project. I like it because it's very similar. I see many applications of the same principle in different areas, but toilet paper will be my example. So yeah, it is my.
I always remember that in European history anyway, the greatest life-saving invention was not anything a medical doctor ever came up with. It's the guys who invented the sewers. And that's what saved the lives.
Okay. Okay, thanks. Good to know.
I just remember another unique project we had, and I don't remember last time. And of course, it was this French student who was designing a device where it would tell you about so it was a smart wine glass that would give you the proper temperature that you should be drinking that wine.
Typical French. Yep.
Yeah.
Alrighty. Well, thanks everyone for joining us tonight. If you feel like a different view on the subjects tonight, the one this morning actually ran for an entire hour before we stopped. And a few different things covered in there. It's up on YouTube already, so if you feel like it, you can go and listen to everything again with a slightly different view on the matters. All right. Well, keep in contact. If you need anything, let us know. The email's there and waiting. Ask any question you like, and we'll see if we can answer it. All right. Bye all.
Thank you, everyone.
I'll stop the recording.
Thanks. Bye.
Thank you. Bye.
Thank you.